This meeting is being recorded.
For problem 18 from chapter 5, we're given some information about some asymmetric syntheses process that can employ an enzyme which would favor production of one enantiomer over another. So we've seen the R and the S enantiomers. Sometimes one can be more desirable than the other. So in this scenario here, baker's yeast was used as our enzyme to convert this diketone shown here. So we have those two ketone groups here into alcohol 1, which is called compound 1 here. And we're given some information such as the percent EE, or the enantiomeric excess of 84%. We're also given the pure S enantiomers specific rotation as positive 88.6. And we're asked to calculate our expected specific rotation for the sample one that was used to synthesize with baker's yeast. So what would the specific rotation for this compound be? So let's break this down, and let's first take a look at the equation that we can use to solve this. So we've seen before that the specific rotation has been given in this type of notation, and that would equal our oh, I'm sorry, let's see here. Rather, we would have our percent enantiomeric excess would equal the specific rotation of our mixture divided by our specific rotation of our pure enantiomer times 100. So this is the equation that we can use. We can plug it in and solve for the rotation of our mixture. So if we were to rearrange this, we can multiply both sides by the alpha of the pure and then divide by 100. So it would look something like this rearranged. The percent enantiomeric excess times our alpha pure divided by 100% would give us the alpha of our mixture, and the magnitude of our specific rotation for compound 1 could then be calculated by plugging in these values. So let's see what that would be. So our percent EE, that was given as 84%. We'll plug that in, and then we have our alpha of our pure, that's positive 88.6. So we'll plug that in next, and then we have divided by 100%. So our percentages cancel out, and we see if we plug these numbers in, we would get about 77 or 74.4. But with rounding to only 2 sig figs because of this 84%, we would see that our magnitude would then be 74. But we also need to determine the sign of the specific rotation, either positive or negative. And we're told that the pure S enantiomer is a positive rotation, or the S enantiomer is dextrorotary. So we can take a look at this compound 1 here, and if we were to determine its configuration, we would see this is our group 1, this is our group 2 over here. This would be our group 3 over here. So this is an R enantiomer, right? This would be, because we know that our hydrogen is our group 4. Our lowest priority is already on a dash. So this will be an R configuration. So if the S is the positive enantiomer, our R configuration would tell us that this specific rotation is negative, and this compound specifically would have a negative 74.